Hi, all right. In this video, we're going to talk about number-based conversions. So this is the final topic in the first week. I'm going to share my screen so you can see what I'm talking about. If today is talk about number-based conversions, we're going to talk about binary, decimal, and hexadecimal. And then there are 2 quizzes over those conversions. Those quizzes are very short. I think they're like 5 questions each or something like that. So it shouldn't take a very long time to do. There are some instructions in here. There are some like PDFs, and you could go through and read those instructions, and that could be helpful to you. You could also go online and just watch YouTube videos. There are lots of videos out there about converting between these number bases. That's because it is a very common thing to do for computer scientists and programmers to need to know that. So there's lots of resources available online to help you out with it as well. Or you can just finish watching this video. But if you already know how to convert number bases, maybe you learned it in CS1 or you learned it from some other reason, you can skip this video and just go ahead and take your quizzes as long as you understand how to go between those 3 bases. Those are the only 3 we will cover in digital. So if you're wondering what this has to do with computers or technology, why are we covering, number-based systems in this class? It has to do with the way data and information is stored on a computer. So you might already know that information is stored on a computer in zeros and ones. It might not be as clear how the computer does that. Like, how do you translate, words and sentences that we're used to, typing, when you write an email, you don't write it in zeros and ones, you type out words. So how does the computer translate that? And it might not also be clear why we do it, why the computer stores things in zeros and ones, and we need to understand how to convert it anyway. Like, what's the point of that? So just very briefly, just kind of like high overview, there is a table. It's called the ASCII code, ASCII. It's the American Standard Code for Information Interchange, I do believe. And it said it takes all of the possible characters that you can type, and it has a number equivalent for each one. So like a capital A is 65, and then a capital B is 66, and it goes through the whole alphabet. A lowercase a is 97, a lowercase b is 98, and it goes through. It has the numbers 0 through 9. It has all the characters you can type on a keyboard. And now it has expanded. We have Unicode now to include characters from all different languages from all around the world. And we even have like emojis, anything that you can type. It has a code in this great big table that says, if you want to display this particular character in any sort of computer application, the computer knows, it has a compiler that can translate that and say, oh, this character is the number 65. I can represent a capital A with the number 65. I will store the A as a 65, but I'm going to store it in binary, in base 2, not in regular base 10, what we are used to. And so when you work in binary, bi meaning 2, there are only 2 possible digits in binary, a 0 and a 1, 2 digits. And so it would convert the 65 to binary, and that way it stores all the information in zeros and ones. If that's something that you're interested in knowing more about, there are millions of videos online and books you can read, or maybe come into the Zoom chat and we can talk about it more. The other question, why do we do it? Why do you have to store everything in zeros and ones? If we have a table that says a capital A is 65, why not just store it as a 65? Why do we need to use binary at all? And the reason they did that is they found that when you're sending signals in the computer, the way the computer stores data, is it has little switches inside of the circuits, and it'll say I'm either sending a signal or I am not. And that's how it can send information. And they found that when they tried to use base 10 signals, it was very unreliable and it was very difficult to tell the difference, to determine the difference between I was trying to send a 3, a 4, a 5, a 6. Like it was hard to tell the difference between different numbers that were very close together based only on how strong the signal was, especially because the signal would like weaken as it traveled. So they found that they were really expensive switches. The computers didn't work really well. There were lots of bugs that had to do with like the hardware and the architecture of it. It was much more reliable and it was much simpler and it was much cheaper to be able to use a system, a transmission system that only had 2 states, on and off. That's it. Either a 1, which represented on, said, I am sending you a pulse. Ta-da, I turned it on, got my little, electricity going through there, and your receiver either says, oh, I got a pulse, so that's a 1, or nothing, 0, turned off. And that was very reliable. And so we had much fewer errors that way. We were able to make cheap we were able to use cheap little switches, and we were able to send signals very, very quickly because they could go really fast and they could be very reliable. So again, just very high level overview. That is why we use binary numbers when we're working with computers, because computers store data and information in binary, and we do that by converting numbers and symbols and emojis and anything that you could possibly type into a number based on that, Unicode chart. And then we use binary numbers instead of base 10 because it's more reliable to send signals that way, as opposed to trying to determine, the difference between very close ranges. Okay, so then we'll go ahead and get started on how do you do it? How do you convert a number from base 10 to binary? What does that mean? And also from binary to hexadecimal, which is base 16. So, first of all, what are number bases? What does that mean? So I'm going to go kind of way back, and I promise there's a reason for it. It'll make sense. You'll see why I went through all of this in a minute. I'm going to go all the way back to probably when you were in like 2nd or 3rd grade and you started learning place values. And you learned how to represent larger numbers in base 10. We use base 10. Base 10 is decimal. That's the decimal number base system. So I guess I can just sort of type this out here for a second. So like we traditionally use the decimal number base system, which is considered base 10. Why do we call it base 10? Because the way we get every one of our place values, the way we figure out how much each individual digit is worth is it has a base of 10. And then we take that base 10 and we raise it to different exponents. It has different powers. So I'll give you kind of a visual of what I'm talking about here. So let's say that if you were to represent a number, we'll say like a 3-digit number. Oh, that's a terrible. Like a 3-digit number, like 348. And when you were back in elementary school, you learned how to represent this 3-digit number. And you learned that this was your ones place, and this was your tens place, and this was your 100s place. Well, what's the pattern there? If I'm going from 1, 10, 100, 1,000, 10,000, 100,000, what am I doing every time to get that next place value? I'm multiplying by 10, right? What we're really doing is we're taking a base of 10 every time, and the only thing we're changing is the exponent. Any number to the power of 0 is 1. That's just kind of a mathematical rule. If you remember your exponent rules from probably high school, any base raised to the power of 0 equals 1. So if I have a base 10 and I raise it to the 0 power, 10 to the 0, my first digit is my ones place. Here, I'm going to increase my exponent. 10 to the power of 1 is 10. So the next digit over here is the tens place. I'm going to increase my exponent again. 10 to the power of 2 is 100. So this third column over here on the left is my hundreds place. Every time I add a new place value, I'm increasing my exponent. I'm multiplying my base 10 up to another power. And then if I said, okay, well, how do I know how much these numbers are worth? Well, you have, I'm going to change the color here. Let's do green. That's pretty. You have 3 hundreds, which means this first number is worth, this first little 3 in that place is worth 300. And then you have a 4 in the tens place. So what I'm doing is multiplying them together, right? 4 times 10 means this 4 is really worth 40. So it's whatever your value is times its place value. How much is it worth? And then finally, we have an 8 in the ones place. And 8 times 1 is 8. So how much is this number worth altogether? We've got, no, go away, I wanted the black. You've got 300 plus 40 plus 8 equals 348. And if you're kind of rolling your eyes right now, like, yes, I remember place value. Why are you talking about this in a college class? It's because the way we do this, the way we say that I use place value to determine how much each individual digit is worth is the same for any number-based system. So it doesn't matter if we're talking about binary numbers, which are base 2, or if we're talking about octal, which is base 8, or hexadecimal, which is base 16, or any number that you can think of or imagine. You could use any number as your base. It just so happens that we've grown up using base 10. And the reason our society is based on base 10 is because we have 10 fingers. So whenever we were trying to do math and count and keep track of things, you know, back before we sort of had formal systems, 10 was the easiest way that we could group things and keep track of them. And how convenient for us, because it winds up being a really nice, simple base to work in. Or maybe I only think that because it's what I've grown up doing, but it seems more simple than some of the other ones. What I'm going to show you next that is going to play off of this same idea is, I want to erase all of this, and I don't know an easy way to do that in Paint, so I'm going to see if I can just draw a big giant rectangle over it. That seemed to work okay. So what we're going to talk about next are binary numbers. So, oh, yes, that's very helpful, isn't it? We're going to talk about next are binary numbers, which are base 2. So instead of having 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, to get our place values of 1, 10, 100, 1,000, 10,000, 100,000, what we're going to have instead is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. Our base is going to be the number 2, And our place values will just be 2 multiplied repeatedly. 2 times 2 times 2 times 2 times 2. That's how we're going to get how much each one is worth. So let's have, we're going to say 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 4. Nope, just kidding. 2 to the power of 3. I swear I know how to count. I've been a computer science and a math teacher for like 11 years. I promise you I know how to count to 3. 2 to the power of 4, yada, 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 yada. And what we get here are our place values. Remember that any number raised to the power of 0 is 1. So my very first digit is my ones place. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. 2 to the power of 4 is 16. So here I have my place values, right? And I'm going to get those numbers by multiplying by 2. Now my place values are worth 1, 2, 4, 8, 16, 32, 64, 128. 128 is probably the biggest that you would traditionally use in computer science because we kind of chunk data into 8 bits. We call it a byte. But you can just keep going by just continuing to multiply by 2. So you can get 256, 512, 1024, 1048. You know, just keep multiplying by 2 and you'll get the next place value up. Okay. So in place 10, when we talk about our decimal numbers, a single digit could be the numbers 0 through 9, right? If I want to try and represent a number larger than 9, I can't do that in a single digit. I would have to regroup. If I wanted to represent a number larger than 9 in base 10, I would have to say I have 1 in the tens place. I would need 2 digits to do that. I couldn't do that with one single digit, right? So what do you think is the largest digit that I could put in a binary number, a base 2 number? Base 2 is very interesting. It kind of takes a little different way of thinking about it than we're used to thinking about numbers. The only numbers, the only values I can have as a single digit in base 2 is a 0 or a 1. If you wanted to represent the number 2, how do you do that, right? All you can have is a 0 or a 1. So let's take a look at how we could represent some of these numbers. Remember our 348. 3 in the hundreds place, you multiply them together, 300. 4 in the tens place, 4 times 10, 40. 8 in the ones place, 8 times 1, 8. 348. We get the values by multiplying together the digit and the place value. So I could either have a 0 right here, and that would just be the number 0. I could have a 1 right here, and that would be the number 1. Easy peasy. But if my only possible digits are a 0 and a 1, how do I represent 2? Right? I can't write the number 2. I do not have that as a possible digit. If I wanted to have the number 2, I would have to say include the 2's place. I would have to go up and regroup. This says I have one number in the 2's place. So here, if I wanted to say I have 1, 2, and nothing else, well, 1 times 2 is 2. 0 times 1 is 0. 2 plus 0. This equals the number 2 in binary. There's kind of like a nerd joke. I have it on a t-shirt. It's pretty bad. It's like there are 10 people. There are only 10 people in this world, those who understand binary and those who don't. because 1 0 is going to be 2 in binary, right? Because I have 1 in the 2's place and nothing else. So how could I represent the number 3? Well, if I wanted a 3, I would need a 2 and a 1. 2 plus 1, 3. What if I wanted to represent the number 4? Well, then I need to come up here to the 4's place. And then I wouldn't need anything else. So these would be zeros. You do have to have those zeros in as placeholders. If you didn't have those, it would just look like a 1, right? Kind of like if I wanted to represent the number 100 in base 10, I do need those zeros as my placeholders. So in binary, in base 2, this is actually the number 4. I have 1 in the 4's place, and I have nothing else. I could say 4 plus 1 to make the number 5. I could say 4 plus 2 to make the number 6. Or I could say 4 plus 2 plus 1 to make the number 7. You can kind of tell that like I'm full here, right? Everything already has a 1. I've kind of represented as much as I can with those 3 digits. So I'm at 7. That was kind of as large as I was able to get with these 3 digits. If I wanted to try to represent an 8, what do? I'm going to have to regroup. So I have this little kind of chart here that might make it easier to see, to kind of understand that. So here, you know, is like the base 10 representation. And here is the binary representation, the base 2 representation. So what I would recommend is when you're trying to convert, write down your place values. And remember, how do I get those place values? It's your base is 2. So just write a 2 for all of them. And then the only thing that's going to change is your exponents are going to go up, exactly like it is in base 10. So any number to the power of 0, 1. Okay. And then all I'm doing here is just going to be multiplying by 2 to get the next numbers. So 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. Times 2 is 16. Times 2 is 32. Times 2 is 64. Times 2 is 128. These are my place values. If I wanted to represent the number 68, which would be if a capital A is 65, then the number 68 would be a capital D. That would be the character that we were trying to store in the computer. How would I do that? Well, do I need 128 if I'm trying to store 68? No, that's too big, right? Do I need 64? Yes, I do. See what I mean by that? Like if I told you to try, if you were trying to represent the number 384, you would not need anything in the thousands place, right? Because that's bigger than the value that you need. If I'm trying to represent 68, I don't need 128. That's bigger than what I'm trying to represent. But I do need a 64. If I'm trying to represent 68 and I already have 64 accounted for, how much more do I need? 4 more. And you could find those numbers just by subtracting, right? 68, your target, minus 64, how much you already have accounted for, is 4 left over. So that means that I already have everything. All the rest of these should just be empty. So I can just fill them in with zeros because I don't need those values, right? I just have zeros in there as placeholders. So like if you were going to do 105, if you wanted to kind of test yourself, you could maybe pause the video, see if you were able to figure this out on your own, and then come back and see if you were right. If I wanted to represent 105, I do not need 128 because that's bigger than what I want. But I do need a 64. So if I say, what is 105 minus 64? I need 41 more. So I do need a 32. 32 plus 8 would give me 40, which means I would only need one more. These are the numbers that I want. I do not need any others, so I can just fill them in with zeros. I don't care if you use a calculator on these things, that's fine. I'm not trying to test your mental math or whatever. I'm not interested in that. I'm more interested if you understand the concept, you know how to do it. And here is an example of, we do need a 128 because 151 is larger than that. So we'll do this as kind of just like a last one. So I have 151, I'm going to subtract 128. So I would need 23 more. So 23 more, 16 would leave me with 7 away. So I would not need an 8, but I would need everything else. And if you want to check yourself, because like I don't feel super confident on that one, the easiest way to check would be go through and add the numbers up. If I go through and write 300 plus 40 plus 8, I'm going to go through and add all the numbers up and make sure that I did it correctly. So I have 1 plus 2 plus 4. I'm going to skip this one because there's a 0. I'll say plus 16. Skip these because there are zeros, plus 128, and I got 151. So good. I think that's kind of the way that PDF does it, is it kind of shows you, make your place values. If there's a 1, you add it. If there's a 0, you can just cross it off. So let's try some that go the other way. Let's say just like some random binary numbers here. If I gave you the binary, could you convert it to base 10? This one's kind of easy. I think you just go through wherever there's a 1, you add it up. So this would be like 2 plus 8 plus 32 plus 128. So the way I would do that is I would say 32 plus 8 is 40. And I would say 128 plus 2 is 130. Ooh, it's raining good outside now. So I have, this was 170. We'll do one more. We'll do the other way. I'll say 0, 1, 0, 1, 0, 1, 0, 1. So again, if it has a 0, you don't need to add it, right? Because I'm multiplying the numbers by the place value, and 0 times anything is just 0. So I can just ignore that. So here I have 64 plus 16 plus 4 plus 1. So I would say 16 plus 4 is 20. And I would say 64 plus 1 is 65. So when I add those together, I get 85. And that is how you convert from decimal to binary and from binary to decimal. There's a shortcut way that you can do it by dividing. You can take a number and you can repeatedly divide it. That's down here on this paper. You can take a number and just divide it over and over and look at your remainders. The R stands for your remainder. And then to get your final answer, this one here, they just kind of, you read them from last to first. So that's another shortcut way to do it. But if you don't really feel comfortable with base conversions, I would just stick to the place value way, because you're guaranteed that you'll get it right. You know, it's easier to kind of keep this one straight. And also it works the same for between base 2 and base 16. Okay. So the final thing that we are going to talk about is base 16, hexadecimal. That's the last number base that we have. I'm going to try and clear my little screen off again. And then, yep, that worked out pretty well. And then we'll type here, the final one is hexadecimal. I did it again. 5 seconds ago. Learn. Okay, let's try this again. hexadecimal, which is base 16. And I want that to be all in the same. Much better. So if you think, decimal is base 10, hexa 6, okay, hexadecimal base 16. Why do we use base 16? We found that, or not we, I was not around at this time, because this all comes from, long time ago, like the number-based systems and the way we store data on the computer, that's been around since the 50s and the 60s. I mean, these topics are all like 60 years old. These concepts are. So whenever I say we, I'm not that old. I wasn't around when this stuff was being invented. But computer scientists do not store information in base 16 in computers, but they found that it was easier to use that to represent binary numbers, because when you have to have 8 binary numbers to represent one single digit, think about how much data you're transmitting. Think about to write one word, to write one sentence, how many zeros and ones it would take to represent all of the data that we have stored. And so when you're trying to read it and write it, and they're trying to go through and have like a program that is written in machine language that's all in zeros and ones, it became really difficult to read, and it became really easy to make a mistake. If you're like 0 1 0 0 1 0 1 0, and that was just one single character, and you've got to go through 15 more to make like 2 or 3 words, that's very time consuming, very tedious. So they said, okay, we can represent 4. Oh yeah, I'm still on my little boxes here. I'm going to do that. I forgot that I did that earlier too. Nothing if not consistent, I guess. They said, okay, well, we can use 4 binary numbers, and we could represent it in one single hexadecimal value. The reason that works, the reason we can group things together like that, is because 2 to the power of 4, that's trying really hard to be an exponent, is equal to 16. So we could say, okay, if I have a binary number, if I have zeros and ones in base 2, I can group them together in groups of 4, and I can get just one single hexadecimal value, one base 16 number. So instead of having to say 1010, I can literally just say A, and I can have one digit and represent 4 numbers instead. So you're taking the amount of information, the amount of numbers that you have to represent your data, and you're cutting it to 1/4 of the previous size. So that's much more efficient. So we already kind of know how these bases are represented, right? We talked about it before. We know that if it is base 16, what that really means is I'm going to have 16 as my bases, and I'm going to have multiple ones. And the only thing that will change each time is my exponent. So I will have 16 to the power of 0, 16 to the power of 1, 16 to the power of 2. And then what does that really mean? Well, we've said it multiple times. Any number to the power of 0 is 1. So your very first value is your ones place. That's going to be true of any number base, right? If any number to the power of 0 is 1, then no matter what number base you're working in, the first digit will always be 1. Okay. Here I have 16 to the power of 1. Well, 16 to the power of 1 is just 16. And here I have 16 squared. So 16 times 16 is 256, right? So it's the same as all the others. Place values in place 10. Place values in base 10, 1, 10, 100, 1,000, you multiply by 10. Place values in base 2. 1, 2, 4, 8, 16, you multiply by 2. Place values in base 16, 1, 16, 256, you multiply by 16ths. Okay. So I could have like a 1, a 2, and a 7. And that would be, I would multiply them together to get their values. That would be 256 plus 32 plus 7. And I could add those together to get the base 10 number. Okay. So that is how you could go between hexadecimal and decimal. That one's a little bit harder. And it's a little bit harder for 2 reasons. Number one, it's not fun to be multiplying together 16 and 256 by all these different numbers and adding them up. The math is not nice and simple like it is when you're dealing with base 10. The other reason it's not so nice is we have an issue that we did not have before with base 2. With base 2, we said you're only, a single digit you only have 2 options. So it's 0 and 1, okay? In base 16, a single digit can have 16 options. So now instead of our issue being that we were very limited, now we have so many options, we don't have enough numbers to represent them all, right? Because when we deal with base 10, we can only go up to the number 9. And if I want to try to represent 10, I have to regroup. I have to have a 1, 0. I need a second digit to do that. I have to go to the next place value. I cannot write 10 as a single digit in base 10. But in hexadecimal, 10, 11, 12, 13, 14, and 15 all belong right here, right? I don't regroup and go up to the next place value until I get to 16. So I have this issue of, how do I represent an 11? How do I represent a 14 as one single digit? And what people came up with is to use letters. We use letters of the alphabet. So if I want to represent a 10, I do that with an A. An 11 is a B. A 12 is a C. I need more room because I'm writing way too big here. So we'll say, okay, and then we can just go back to writing. A 13 is a D, 14 is an E, and 15 is an F. And I like to say that F is for full because that is the biggest that you can get. You could not represent more than 15 in one single digit, because if you got to 16, well, remember, we're in base 16. If I get to 16, that means I need to regroup. I need to put a 1 in a 16's place and then nothing else. 1, 0 would be a 16 and nothing else. So a couple of things to kind of be mindful of when you're dealing in hexadecimal. And a big one is going to be this right here. I would recommend you write this down in your notes, kind of put that somewhere handy to keep track of, because that's something that you will see and you will need to know and be able to use that. So in hexadecimal, you can represent numbers 0 through 15 as one single digit. And our place values are 1, 16, 256. We won't ever deal with any numbers that require place values larger than that, beyond that. But if you just wanted to do it for kicks and giggles, you would just multiply 256 by 16 to keep going and get the larger place values. Okay. So let's do some conversion examples here. I'm going to take all these away. All right, so and let's take a decimal number and we'll convert it to hexadecimal. So let's say I had, I'm always going to start with my place values. I always start by writing down my place values. So I know that my place values are going to be 1, whoops, might help if I change the color, 1, 16, and 256. So let's say that I asked you guys to represent the number 500 in base 16. Okay, so I'm going to use the calculator on my phone because I'm not going to, y'all are allowed to use the calculator too. That's okay. You don't have to do mental math for it. So I'm going to say, okay, my target is the number 15. Do I need a 256? Yes, I do. And I will only be able to hold one of them, right? Because if I had 2 of them, that would be greater than 500. That would not make sense. So I started with 500 and I have 256 accounted for. So I'm going to subtract 500 minus, I've already got 256 right here. I need 244 more. So how many 16s do I need for 244? Kind of what operation would we need to do to figure that out, right? If I'm trying to say what is the largest amount of 16s that would go into 244. See if you can kind of think about it. Pause the video if you need to before I kind of tell you the answer. So you would divide. So we would say, I'm trying to get to 244. How many 16s do I need? I need 15 16s. Well, how can I represent 15? You've got to remember your alphabet, right? A is 10, B is 11, C is 12, F for full. F is 15. It's the largest number we can represent as a single digit. Okay, so if I wanted to say, how much do we have right now? 2 times 256. I'm going to change the color for this. This is worth 256. What is 15 times 16, right? That's what I have right here. 15 times its place value. That's 240. Okay, so how much do we have so far? 240 plus 256 is 496. How far away are we from our target of 500? I need, I'm gonna go back to blue. I need 4 more. Okay. 4 times 1 is 4. I add them all up, I get 500. It's the exact same concept that we use in binary. It's the exact same concept that we use in base 10. It's harder than doing the other ones only because, truly only because multiplying by 16 sucks, multiplying by 256 sucks, and trying to remember the A, B, C, D, E, F is hard. So personally, like me, I don't like going between decimal and hexadecimal, and I really don't ever do it that way. Me personally, I think that going between decimal and binary is easy. And I think going between binary and hexadecimal is easy. So when I am doing number-based conversions, I don't go between decimal and hex. I go to binary first, and then I go from binary to base 2. And I'll show you why. I'll show you how much easier it is to do that. So the reason that I think it is easier to go between binary and hexadecimal is we have that really nifty grouping shortcut I told you about earlier. Let's say we have a number in binary. So here's a number 10, 10, 1, 1, 1, 0, whatever. And if I asked you to convert that to base 10, you could. You would write all the place values down below it, and you would just add up where the ones are, right? But I am going to ask you to convert it to base 16. Look at how easy it is. We are going to remember that if I'm going from binary, from base 2 to hexadecimal, base 16, I'm going to do so in groupings of 4. Here is a grouping of 4. Here is a grouping of 4. I only consider these 4 digits at a time. So you can almost like just use your hand and just cover up this 1010 over here on the left-hand side, because we're not going to look at it. We're not going to think about it. We're not going to consider it. It's just, I'm ignoring it right now because I only care about 4 at a time. So I'm only going to look at these 4 right here. And my question is, what is that number in binary? Okay, I know how to do that. Place values. Start with place values. This is 1, 2, 4, 8. What is this number? 8 plus 4 is 12, plus 2 is 14. This is the number 14. How do I represent a 14 in hexadecimal? I can say this is equal to E. When I come over here and I look at these 4 digits, I'm going to completely ignore the 4 we already did. The fact that this is farther left, like that's a bigger place value, I don't care. Don't think about it. Use your hand, cover up the 1110. Don't even look about it. We don't care. We are looking at 4 digits at a time. So I say, what is this number? Start with your place value. This is 1, 2, 4, 8. What numbers do I have? 8 plus 2. This is the number 10. Well, how do I represent a 10 in hexadecimal? Okay. So if I gave you this number, if I said 10101110, that's a binary number, and I asked you to convert that to hexadecimal, the answer would be A, E, American Eagle. That's it. Right? Because these 4 digits were an A, so we'll kind of do a little coloring. These 4 digits were an A, and this is over here on the left, so it goes over here on the left. And then these 4 digits were an E, and that was over here on the right, so that goes over here on the right. The answer was AE. And that's everything. That is going from base 10 to base 2 and back, from base 10 to base 16 and back, and from base 2 to base 16, which I think is a lot easier. And so that's why I always like to do it that way. If you kind of felt like, if you don't feel great about this, a couple of things you could do. Go through those PDFs that are in D2L. I think those are helpful. Dr. Johnson created those, and they kind of have all the steps and instructions. I think that will help. Look online. There are so many YouTube videos where people go through this. These are very common concepts to know and use. There are lots of instructional material. There are lots of games, like practice games you can get on and play to try to get like fast at them. Online and play those games, those quick practice games, you get to where you increase your fluency, where you really don't even have to think about it anymore. You know, if I see like 1011, I don't do the math in my head. I just know like, oh, that's 11, that's a B. And when you can do that, it makes it where you don't get bogged down so much in trying to do every single little math, because you just kind of get more practice with it. Just kind of, it comes to you more naturally. If you're not a computer science major and you don't think that you will ever do this again in your life, then it's not worth your time to try, you know, practicing them and memorizing them. You just need to write down your place values and use your calculator and multiply things out and just, you know, get through your 2 quizzes and the questions on the exam, and you're done and you can move on. But if you are going into computer science, I do think that knowing your number bases is really important. It is there are lots of foundational concepts that are based on them, and you will use it again, especially like in architecture, you see it in those places a lot. And so if you still have questions after kind of going through that PDF and maybe watching some videos online, if you still don't feel good, try and come to the Zoom meeting. I'll be, online for an hour, and we can work through practice questions. We can go through it one-on-one. I think it probably is a little clearer whenever I teach this in a classroom and people can stop me and ask questions. You're really not getting the benefit of that right now, just watching these videos. So if you do have questions about it, come to the Zoom meeting. We'll go through it together, and I will be happy to help you out, and we can work through problems together. I think it'll make a lot of sense. You guys have a great weekend. You were through with all of the content for week 1. So I will see you back next week for we start Python. Yay. I'll see you then.